Okay, right. Welcome, ladies, gentlemen, children, animals, everyone, to the Real Robotics Lab for the first of our demos for Robot Lab Live. So I'm joined today by Nick Castledine and George Jackson Mills, doctors in both cases, postdocs working in the lab here. And yeah, you want to just quickly introduce yourselves and say a little bit about the projects that you're representing?
Yeah. You go first, George?
Yep. I think he does.
Hi, I'm George. I work on TACPOTS, which is a project to use miniature robots to investigate the water and waste water network in the UK, looking for defects and replacement of existing pipes.
Cool. And you, Nick?
Yes, I'd love to. Hi, I'm Nick. I'm working on the VEAN project, which is robots and AI in nuclear. So it's looking at nuclear robotic solutions to kind of aid with the decommissioning of nuclear sites around the UK and around the world, in fact.
Cool. Okay. Yeah. And yeah, that's sort of part of generally a lot of what we do here in the Real Robotics Lab is sort of essentially inspection robots, robots for inspecting things where people can't easily go, don't want to go, stuff like that. So, shall we start, Nick, with PyBear?
Yes.
So
this is the robot I've been working on. It's designed for use within 2-inch bore pipes, specifically 2-inch bore pipes up at the Sellafield site, as they have lots of pipe up there which they're not quite sure what's in it. They don't know how radioactive it is, they don't know what contaminants up there. So it kind of makes the whole decommissioning process, removing a section of pipes and disposing of them safely, quite difficult. So the aim of this robot is it's going to go into the pipes. There's going to be a radiation sensor attached behind it. It's going to move through the length of the pipe, detecting how radioactive the pipe is, and it'll report that back to the base station so people then know how to safely dispose of that pipe. And there's also a camera on the front, it's a very tiny camera. I think we have a feed for that.
Oh, wow, that is tiny.
So we do have a feed for that. Let me enable the feed for that. There we go.
So this allows us to see if there's any blockages in the pipe, if there's any damage to the inside of the walls, or any kind of like areas of like flushing material or contaminants there.
So it's worth noting that this is a fairly early stage low TRL prototype that is mainly aimed to assess and develop the locomotion capability of this robot. So it doesn't have a radiation sensor on it yet, and we haven't worried about radiation hardening and stuff like that yet. And also maybe worth noting that it's sort of ultimately being designed as a disposable type thing. Yeah, Nick?
Yes, so it's designed to be a single-use robot, as it's going into a nuclear
highly contaminated,
which could be highly contaminated with radioactive materials, and that does not play nicely with electronics. It's got a habit of destroying them very quickly. And also wheels and the actual chassis of the robot itself might pick up radioactive contaminants.
Yeah, it would be very hard to decontaminate.
So it's designed to be kind of as cheap as possible, so we can put it into the pipe, we can pull it out and just dispose of it and use a new robot for the next pipe run.
Yeah.
So it's the type of robot, it's a wall-press design. So there's 6 wheels on each one of these robots. And each robot is driven by a very small DC motor, which is...
He means each wheel.
Can you move the wheels again?
Yeah, we were saying. Wow, cool. So the arms with the wheels on are actuated outwards, they're sprung outwards. So this provides the traction of the wheel against the pipe wall itself. It allows it quite substantial traction. So it's pulled quite a lot of weight through the pipe behind it.
And to be fair, this aspect isn't working right now, but we're going to be able to actively retract the arms to help get around.
Helps it move around T-sections, 90-degree bends, and things like that, which robots on the scale currently can't do. So that's kind of how a robot is not 100% apart from other kind of pipe robots on the scale.
Well, so shall we seek out the proof in the pudding at this point, Nick?
We shall.
Definitely.
So what we have here is a very small pipe network of realistic diameter for the application that we're interested in, but not a realistic material. We've chosen to go with clear acrylic here, basically, so that we can see what's going on inside. But you may notice, show us, George, the mystery area at the end of the pipe.
The danger zone.
It is a potentially dangerous zone there. That's what the red and white striped tape always means, is danger. So we have no idea, not a clue, what is hiding in the pipe there. could be a monster, could be radioactive sludge, could be gold. We're going to send the robot in and go try find out. So as it's quite common within robotics, actually, I think, to use Xbox controllers as the user control. Quite a lot of effort's been put into optimizing them for ergonomics, and they're wireless these days. Whoa! It was just off camera, but Nick so nearly just tripped over the tether for his robot, wiped out, killing himself and destroying the robot in the process. No, I jest. That didn't happen. Okay, so Nick, you want to see if you can go and get for us? All right. So thanks to the wall press mechanism, we've got good friction against the pipe walls. Going just down a straight piece of pipe is easy. The trick is when you get to corners and such like, and that is where, the grinding of the gears. That is where a tiny bit of further improvement is probably required. Come on, Piper, you can do it. So it wouldn't be interesting for you guys if it worked first time every time, of course. What's it snagging on?
I think it's the camera.
The camera, of course. Alia Talat asks, do robots tend to get stuck in such situation? Yeah, very good question. Basically, they need to not get stuck in that situation, which is why we definitely still have some way to go in terms of insurance reliability. That said, there is one actual legitimate reason why it's struggling a little bit here. So the plastic pipe that we're using here has like push fit connections, which means on the inside after that corner there's a lip. Oh no, we've lost a wheel. We have. Oh lordy. But notice how the graceful degradation of this design. We have, it turns out, lost a wheel in the pipe. That's cool. With 5 out of the 6 wheels, we were still able to do a return to base maneuver, no problem at all. Good question about the reliability there. I mean, essentially, this is why you have to do a hell of a lot of lab testing before you try to do a real-world deployment. Don't worry, that's fine. We will have a spare. We have a spare for the final run. Right. Both of the robots that we're showing you today are like hot off the presses or off the printer. So these are all still quite crude early prototypes. So yes, there are all sorts of limitations, all sorts of issues. So like, for example, here we're using clear pipe just so that, we can see what's going on inside. Okay, there you saw the feeler do its job. I'm not sure why it's squeaking so much. I'm sure it's not a problem at all. So for example, if this was actually in a steel pipe, we would need a light source because we wouldn't be getting light inside from outside. Are you managing, Nick?
Let's try again.
Yes, let's try again. I'm sure it'll work this time. Okay, yeah, I think it works better with the robot I view small. Oh, looks like, there we go. He's made it around the corner. And oh my goodness, what is that we see in the distance? I think it is a radioactive duck. And you will notice it is angry and has fangs, which means that is definitely top level waste, needs to go into the dangerous waste stream, definitely. So make a note of that for later. Okay, now we get to see if he can back it out again. Shall we switch across to the other robot that we have to show you guys today?
Here's the other robot. It's the Pipebot's marsupial robot. It's a unitary robotic dog with a swarm of 10 miniature Pipebots attached on top. Here they are, blinking, all ready to go. Beautiful. They're beautiful. We didn't create the robot dog, but we did build all these tiny robots. And the basic idea of this system is that the robot dog can walk the tiny robots to the hard-to-access spaces through the larger bore entrances of the larger pipes, and we find smaller pipes that it can't access, and then we deploy an entire swarm of robots that will go and investigate for us. So why don't we just deploy the swarm right now?
Let's do it.
Ready?
I'm ready.
I'm turning it on.
George's hand, of course, is just there so he can sort of feel any vibrations in the system. He is definitely not actually lowering it manually, because the deployment mechanism definitely didn't actually only get assembled half an hour before the first demo and not work. And he's definitely not manually moving those little robots off the deployment mechanism, because they definitely all work.
All in working order.
All in working order.
They're all being teleoperated by me.
Yes.
And my hands.
But let's get a zoom in on the one in the leader there.
Yeah, they're now ready to investigate our hard to access space, which clearly you couldn't fit a robot dog in. It's a tiny sewer pipe. You can tell by the way it's pristine.
Yeah, transparent. Yeah. Yeah, that's what all sewer pipes look like, actually.
Here he goes.
Look at that cute little robot. Oh. Oh, the poor thing.
Stranded.
Initiate the self-righting mechanism there, guys. There we go. Some refinement required. The googly eyes, of course, are not functional. They're just there for aesthetic purposes. And shame, the poor thing is taking some strain after all of today's demos. There we go. So, yes, so, I mean, we really did put this together and test it like today. It was to the wire. You may notice we had to do a last-minute modification, adding a tail to the back, because our poor little robot ended up being rather more top-heavy than we had envisioned, and so it just rolled over backwards when we tried to drive up the slope. But I think that the current tail is maybe not entirely optimized, but I do think a tail can often do really good things for a robot's locomotion, just like for animals. Tails can add stability, help you with climbing over things and all sorts. But yeah, so as you can see, some work is still required, but it's got quite capable locomotion for such a small robot. And also, the astute viewer might have guessed maybe at this point that there's some teleoperation going on right now. But the electronics payload on these robots is comfortably enough to do autonomous control, autonomous behavior, and ultimately for swarm deployments, it kind of has to be that way. But yeah, no, so that now that we've added the stabilizing tail, it's pretty decent locomotion capabilities, some room for improvement, but certainly more capable of real-world operation than most swarm platforms. I noticed that the other robots, while we weren't looking, moved into position.
Well, when did that happen?
Whoa! Bad editing on my part. I think they're kind of shy, and they don't want to move when the camera's looking at them.
Autonomously explored this pipe while we weren't looking.
They have completely 100% autonomously explored that pipe while you weren't looking.
Unbelievable.
Yep. And now that you're looking, they're freezing because they're scared.
Bit shy.
Okie dokie, folks. So that kind of gives you a sense of the long-term vision here with the heterogeneous swarm marsupial approach.
Yeah.
Because of course tiny little robots can't move very fast, stuff like that. Big robots can much more easily cover longer distances. So the notion of using large robots to just deploy small robots into areas that the big one can't get into is, I think, quite interesting.
And this marsupial design it's pretty rare, and no one's ever done this with a robot dog before, especially with like miniature robots on this scale.
Yeah, I think that is quite possibly true.
And basically, there's 10 robots that have been deployed on this side, and then they've gone off and explored the pipe. But in the end, we're going to have a mirror of this mechanism, and there's going to be another 10 on the other side. So it's 20 robots on one dog, and they'll all be deployed at once, or one side at a time if it's a smaller pipe. Allowing for a full swarm to just come pouring out.
And I mean, I think to be fair, there is some room for optimization in the deployment mechanism such that we could do more than 20 at some point in the future.
Yeah, you could have like a carousel kind of Ferris wheel.
Yeah, Pez dispenser.
All sorts of options. Put them in a bucket and just...
There's wheels on there, George.
These aren't wheels, Nick.
Good question.
Of WEGs, the new thing.
Whoa. Can you tell me more?
So these are wheel legs. Wow. So basically, they're sort of a circular profile, right? But with loads cut away. So you've got 3 spikes. You can have different numbers, like 4 or 5. And the basic idea is that instead of wheels, which are perfectly round and you just kind of bump up your obstacle, these kind of have hooks and teeth on the end, and they can climb and crawl their way up, which allows them to move over obstacles that are...
Better stair climbing capabilities.
Bit of climbing ability versus a wheel design.
While still being just as simple as a wheel to actuate, it's just 1 degree of freedom per unit.
And they also look a lot cooler.
They do look quite a lot cooler. Do we have anybody in the audience, full stop, and would any of said people like to ask us any questions? George and Nico, you guys,
we're trying to read the questions.
Yeah, how do I do that again? Right, so Will Shepherd has posted radioactive duck ? Yeah, I think it is a radioactive duck, and we better be really careful. It probably does. We have an excellent question. Claire Asher asks, I might have missed it, but how would you control lots of these robots simultaneously as a swarm? That is an excellent question, Claire. So that suggests that you did notice that we were teleoperating today, which is quite often done in robotics, but to be honest, it's not our intention for these. Ultimately, the whole swarm needs to be autonomous. Swarm robotics, by definition, is autonomous, a subset of autonomous robotics. There is plenty of processing power on the electronics package in that little robot to give quite high-level autonomy. Probably not to do like sort of simultaneous localization and mapping in real time and stuff like that, but it's going to be sensorized and able to do some reasonably advanced autonomy. Swarm robot autonomy is generally sort of insect level intelligence rather than human level intelligence. But yeah, because indeed driving them all manually would not be feasible. Okay, some guy called Rob Richardson. Rob is actually Rob's my colleague, Professor Rob Richardson from the lab. How do you stop the big robot falling over the little robots? That's actually a pretty good question. Do you mean like not I think he means like not tripping over. How do we stop the little robots from tripping up the big dog? Yeah.
Oh, right. The big dog will just squash the little robot.
Yes. I think the concern would more be for the safety of the little robots were they to. But no, so I mean the plan. So the big robot's not powered up at the moment, but it is shown in its sort of deployment pose, crouching down to make it a bit easier. I will put the hand cam back up. Yep, sorry. There we go. I suppose what we would probably do is have the big robot wait until the little ones have scuttled off into the corners that they're scuttling off into. We've got some more questions. William Westway asks, what's the main aim to map, to detect cracks, to unblock, or maybe all? In the long term, all of those will, For the moment, the Pipebots team isn't really focusing on doing interventions like unblocking. It's more just about pervasive sensing. So mapping is one of the key challenges because as it stands, nobody really knows in much detail what the sewer, network looks like. There's a lot of missing information, out-of-date information. So mapping is one of the key things, and then condition monitoring is, I suppose, the more fancy way that we say crack detection and blockage detection. But yeah, those are two of the main goals. Thank you. Let's see, what's next? Is there an element of learning in the algorithms? Yes. Right. So Steve, the algorithms don't really exist yet in terms of, assuming you mean the algorithms for the behavior of the robots. We haven't gotten that far with these little guys yet. It's a very good question. I imagine. So one of the other themes of the project based in computing is sort of focusing on autonomy. So do you think, George, that we'll do sort of learning on these little robots, or more sort of determine the behavior beforehand?
In terms of looking at different cracks and things in the pipes, I imagine they'll definitely get better at learning.
Yes. So like offline machine learning could certainly be done over time to do better defect characterization.
Yeah,
and in terms
of feeds that we take back from missions that we go out through pipes, we can go back and we can learn from that data. When we've got a data set from one pipe, we can compare it against other pipes. And then basically the way you do a lot of pipe maintenance is feed those back into a massive database of different pipes, looked at different ages, and you compare them against each other to view what kind of condition the pipe is in overall.
Yeah.
And
it
allows you to make an informed decision on whether that pipe needs replacing, which is ultimately the goal for pipe bots.
Yeah. And in terms of the sort of low-level autonomy of the individual swarm members, I think I would imagine that we might do some like evolutionary optimization in simulation beforehand. But I think once the individual robots are deployed, they probably won't be learning in terms of their own behavior. Okay, but thank you, Steve. Eric asks, how many robots in the swarm?
20.
Yeah.
So the fully working 10 aside section, and then this is basically going to be mirrored on the other side of the robot. So there'll be another set of 10 robots on this side, and when they are deployed, they'll be deployed either one side at a time, or you can do both at once, depending on if you're in a large pipe or a smaller area. Because obviously when this mechanism folds out, the robot gets a bit wider, so you might want to do both at once. But you could, all 20.
Yeah, so I mean, I think there's kind of a question around how many robots does it take to make a swarm, and we sort of felt that 20 was about the minimum where you can legitimately call it a swarm. I mean, further down the line, you would hope there'd be hundreds of them. Okay, we've got Jason Liu is asking, how will you tackle battery power in pipes? Yeah, good question.
Basically, we're planning to use the main dog robot as a docking mechanism. So we'll go back, and when the little robots run out of battery, they'll go back in here, and basically where they sit, they'll have like little cables or rails that they dock into, and then they can all charge from those.
Right, so it's sort of a mobile charging station type approach.
I mean, that still doesn't solve the whole power issue. You can't really solve that without having a tether that goes all the way down the pipe.
Yeah.
But basically, if you've got these tiny robots, their battery life is going to be like 10, 20 minutes or something if they're running a lot of processing, which we intend to do. So they're going to need to go back and recharge. But the larger dog robots can hold up to like 10 kilograms. Which means that we can stack it full of batteries, and then essentially drain those batteries and extend our lifetime in the pipe.
What kind of connectivity does or will the pipebot have, particularly considering the environment inside a pipe? That is a very good question, and one that, to be fair, us three aren't the optimal ones to answer, because as part of this project, there's so we're the mechanical engineering theme, mostly looking at the physical platforms. We've got some folks in ElecEng focusing on the connectivity type stuff. George, do you feel happy giving a answer to that?
Not really.
Okay, I'll bring it. So yes, so standard wireless comms, the sort of 3G and Wi-Fi and stuff like that, do not work well at all in buried pipes. I don't fully understand the physics behind why not, but it's something about different the waves like bounce differently off the pipe walls and stuff like that. So for a relatively low bandwidth communication, one of our themes is looking at alternative lower frequency RF methods that might work, should work. And then there are also options, of course, much lower bandwidth, but you can use visible light or infrared light for communication, as well as sound, in fact, sort of like old-fashioned modems, essentially. Yeah, so ultimately the plan is that the individual robots will be able to sort of form ad hoc networks and sort of pass information between each other and onwards to base camp. Oh, here's one that was missed earlier. Sorry. What is the max speed of WEG robots? And how long the operation for one charged battery?
That's a good question.
I mean,
max, Andy. Put it to max.
But it's max, it is max. It's only got one.
It's always been max. You just saw its max speed in its current iteration. But I mean, generally you don't want to go like too
It's
fast.
30 centimeters.
Oh, we're going to have an experiment. Okay.
Well, no, we're going to go 50.
50, so it's easier maths, yeah.
Right, starting there. Go!
1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. Okay, so that's about 5 seconds per half a meter.
That was maybe 10 seconds. That was 11 seconds, though.
Wow. Now put it to max speed, Andy.
That is max speed.
So pretty fast. I mean, there's all sorts of optimization that could be done there. Essentially, it's always a trade-off between speed and torque. If we ultimately find, there we go.
How fast was that?
Question.
Someone thinks they're cute. We agree.
Us or the robots?
I think you guys. I think they mean you guys. And me as well. I think the three of us, we're all pretty cute, aren't we? But no, I suspect that they actually mean the robots, and it's true. And actually, I think, there's real scientific reasons why it is important to make robots look cute, because they have to cohabit with people. People don't like scary, creepy-looking robots. People like nice, cute-looking robots. And so your robots, in all seriousness, are going to see much greater societal, end-user acceptance if they look kind of cute. It's that lag. How to tackle the vertical pipes with the wheel legs. Fortunately, sewers don't have vertical pipes. They do have something even more difficult, which is large vertical gaps.
Yeah, big drops.
Between pipes. Good question. Going down is quite easy. You just need the robot to be robust enough that, boom, doesn't die when it lands.
Yeah. I mean, with WEGs, you've got Nick's option, wall press, which is great for pipes.
Yeah.
It doesn't work great for other non-vertical pipes. There are better methods. You've got things like magnets for adhesion, I guess.
Only works on metal
Works
pipes.
on metal, which doesn't exist in the sewer.
Yep, not much.
And traction's really difficult in the sewer anyway, because it's quite slippy because of all the water.
Yeah, and other things in the water. Yeah. Yeah. No. Indeed. Good question. And I mean, the heterogeny approach, I think, might be a big part of it. It's not out of the question to envision a flying member of the team.
Yeah.
Drop things off, maybe, or a larger robot, with an arm, or possibly for the future, robots themselves could, rather than just being a swarm, they could sort of be a modular swarm, where the individual robots can actually mechanically link with each other in order to form larger robots.
Yeah, that's definitely a cool solution, like mechanically linking or climbing over each other like in a pile, like a biomass of swarm robots that go up a vertical pipe.
Yeah. And we have another actual serious question. How will they keep clean in a sewer? Yeah, good question.
Yes. They don't. They'll get really, really horrifically dirty.
Yeah.
And when they come out, we'll have to clean them.
We need to seal them, I
They'll
suppose.
be sealed, so
Better than they are now,
Contact
yeah.
will be the legs and
The entire body.
chassis
Yeah.
and the entire robot.
Yeah.
The entire robot. But the internals, the important electronics, the battery, they definitely can't be touched with all
Yeah.
the sewage.
So good sealing and then
seal it,
post-operational cleansing.
spray it down, get some Lynx Africa on that robot.
And on that note, I think we are going to say goodbye to you, our dear audience. That's all we've got in us.
Stop moving.